Hey, hello there. So today I'm looking at the question 128, longest consecutive sequence. So we have a unsorted array of integers. We want to find the length of the longest consecutive elements sequence. So since that the elements inside this array are integers, we are looking at a consecutive integer sequence. So it will be something like 1, 2, 3, 4, 5, and we want to find this kind of sequence and the length of the maximum one we can form using the numbers we have. The example, we have an array of 6 numbers, 100, 4, 200, 1, 3, 2. So we actually have 3 different consecutive integer sequence we can form using the 6 numbers. 100 by itself is a single number sequence. 200, same single number sequence. The remainder 4 numbers, they are 1, 2, 3, 4, so they form a sequence of length 4. So notice what we just did is to partitioning the set of numbers into 3 different disjoint subsets. So each subset corresponds to a consecutive integer sequence, and the longest the size for the longest one, it's pretty much the size of the largest subset if we do the set partitioning. So if we think about this way, it's very naturally to think about UnionFind data structure and using UnionFind to solve this. Let's look at the runtime complexity requirement. It has to be in linear time. So does UnionFind fits the requirement? It fits, because the union and find operation, they are almost amortized to be constant, so that we have n elements here. If all we do is just doing some constant multiplier times of union or find operation for each individual element, we are guaranteed that our total runtime will be linear. So the runtime works, and it's very natural to think about UnionFind if we do know about it. So let's talk about how we do the UnionFind. We're just going to initialize the annotation for each element. Notice that if we do, let's just copy this data structure over here so that we can talk about it a little bit. So really quick, how UnionFind works is that we got a bunch of elements here. In my templates, they are from 0 to n-1. We just annotate its parent, which is telling us which subset this element belongs to, and the sizing information for the subset containing each element. So they are length of n. 1, we annotate this for each of the element, and when we do the union, we basically connected the 2 subsets that this 2 element belongs to. The find is just to find the representative for each subset. So with this, all we need to do is just for each element, we're just going to union it with the next number in the sequence, if we do have that at our disposal. So in the end, if we do union 1 to 2, 2 to 3, 3 to 4, we are guaranteed to put all these 4 numbers into the same subset. And since that neither 101 or 201 is inside this array, they're just going to be by themselves a single element subset with this UnionFind. And in the end, since my templates here is the union by size, we have all those sizing information already available during the union operations. So in the end, we just return the maximum numbers we have inside this size. So it will be super simple in terms of code to using UnionFind for this problem. One little modification we need to do is that these numbers are so these numbers here are not 0 to n-1. So there's one thing that I can do to create a mapping from the number to its index inside the array, and just using the index as the accessor to the parents and sizing information to perform this UnionFind. Or we can just the thing that I'm actually just going to do is to convert this into dictionaries hash maps. So it will be a little bit space inefficient, but it doesn't change the fact it's linear in terms of space. Yeah, so I'm just gonna have a simple insert function here to do some kind of initialization. For each element, for each individual number, it's by itself a single element sequence. So I'm returning the sequence representative, maybe the maximum number inside the sequence. If we do really union 1 to 2, 2 to 3, 3 to 4, that will end up with the largest number to be the sequence representative. And the sizing information is just 1. Every one is by itself a single element, single number sequence. But this definitely will change after we do perform the union operations. So yeah, so this is the slight modification to my UnionFine templates. It will work for this question pretty well. So the way we use this is pretty much just initialize this UnionFine data structure with the numbers we have, and for each number, all we're gonna do is to check, do we have the next number in the line? If we do have that, we want to union them to connect them to form a longer consecutive element sequence. We are doing this checking to use the membership, the dictionary keys, because that gives us pretty much a constant access. If we do the checking inside this nums, it will be an array, it will be a linear time check, it will be much more expensive. So we want to actually perform this check with the hash map we have. If for any number, if we do have the next number in the line, we're just gonna union them. So connected these two lines to form a longer consecutive integer number sequence. Num1. So in the end, what we want to return is just the maximum size of the sequence. So that's in the case that we do have those. If it's totally empty, meaning that we have nothing in the array, we return 0. So this is a default here. Or can I just put a 0 here? Let's see. If I have an empty array, does it work? Okay, it's not working. Can I provide a default? Anyway, I'm just gonna do a test and return that if it's not empty. So this should work. Okay, so yeah, so this is the code for UnionFind. If we use UnionFind to solve this problem, we're just going to initialize UnionFind. For every number, the initialization is that they just by themselves a single number sequence. So the length for that sequence is 1, and the leader for that sequence is the number itself. And we're just going to do one pass to initialize this thing. So that's linear in terms of initialization. And then we do another second pass here. For every number, we test if the next number in the line is at no disposal. If that's the case, we do a union so that we pretty much connect the consecutive numbers to form the longest possible consecutive integer sequence they can form, and in the end we just query the size. So that's a working solution in arguably linear time. So look at some optimization we can do. So here the union is actually happening somewhat randomly. So let's say that we have 4 and 1. We actually we're gonna union 4 and 1, and then we union 1 and so for number 4 inside for our code, it's not doing anything. For 1 it's union that with 2, and for 3 it's union with 4, and for 2 it's union with 3. So the order actually it's a little bit messed up, and for that reason it's gonna take longer. The reason being that if we union 2 with 3, 2 will remember that 3 is the number that's leading the sequence. Then if we do union 1 with 2, 2 would tell 1 that 3 is now a leader, so 1 would update its knowledge about the leader to be 3. So this will be a little bit extra work it actually needs to do. So if we perform union in the other order, union 1 with 2, so that 2 knows he is the leader, then union 2 with 3, 2 will just update its own old belief, and it doesn't matter, it doesn't change the nodes 1's belief. And then we union 3 with 4, 3 would just only do the update about his knowledge about the leader for the sequence. So in that sequence, in ordering, when we do the union, it's less work. If we in the worst case we union 3 and 4, then 2 and 3, and 1 and 2. There are more updates we need to do inside the find operation. So one thing we can do is just to control this union ordering a little bit better. So what we're going to do is look at the consecutive sequence. The property for that is it always starts with a number that has no previous number that are at our disposal. So that's our starting point. For every number that has no prior number, we're going to initialize this union 1 with 2, 2 with 3, 3 with 4 until the next number is not something we have. And then next time when we see some number, that's guaranteed that we process this union for all the numbers in the sequence. So that next time when we see number 2, we don't need to even do anything, because it's if we initialize this chain of action when we see the smallest number in the sequence, it's guaranteed that we taking care of the set partitioning. So that will be a little bit less work, but still in the linear time territory, and the runtime may not even be noticeable, but in theory it might be slightly faster. So so if I do have a number that's one smaller than me inside the at our disposal, that means I'm not the first number in the line, so I'm not gonna initialize this chain of actions to connect the numbers together. Otherwise, I would just say if I do have a next number in the line, I do want to do this connection. So this will be a slight modification. Let's see if it works. And it's not faster, but based on this some analysis, this should be slightly more efficient. But anyway, notice that if we look at this solution, then this loop, the number of times this loop runs, actually tell us the size of the sequence. So when we analyze the code, we find that there's really no use of this sizing information, and we don't need to do union by size anymore. All we need to do is just to keep track of how many times this while loops run, and keep running maximum, and in the end just return that maximum number. So that gets rid of the union by size, which can potentially take some more time. And then all we notice here, we don't actually need anything about union anymore if we don't need the sizing information from UnionFind. So all we actually using UnionFind in here is just use it as a set. So so let's just quickly modify that code. So we just convert this into a set then. So yeah, so this is pretty much a so this is pretty much reproducing what the modified version of the UnionFind solution because when we analyze the code, we realize we don't need the sizing information we get from Union. All we're actually doing here is just checking the find, or just checking whether we have the number or not. So this can be reduced into just using a simple set, and just count the number of times we do this while loop. So this will be much faster, and it's actually something that we can derive, or we can reach when we analyzing our UnionFind code. So yeah, it's much faster. Yeah, so just gonna go back to talk about one last thing here. So notice that here we have this array of, readily available. What if these numbers come in sequence? So it's a string. So we're looking at a online algorithm that process elements one at a time, and at any given time of this data structure, we might be running a query to see what's the current longest consecutive sequence that you see. So if that's the case, we don't have this at our disposal in the beginning, and we can't do this. So, but we can still use in UnionFind. Let me just illustrate what this means. So in the initialization, we just don't have that nums information, so it would be totally empty in the beginning. And for each find operation, we can actually do this insert lazily. So that when we have new numbers coming in, we can use the find, or just explicitly calling an insert. It would be fine. Why I'm having this in the find? I don't need it. So yeah, so for that reason, we no longer have this UnionFind to operate on, initialized with the numbers we have. They're gonna come into in a string, and we process them one at a time. And so the thing that we do is just check the number that's one larger and check the number that's one smaller, and do this union. the reason that now in the online version we check both sides is we don't know which number we already had. So so that's why we need to check both directions. If the new number coming in can actually bridge those, we want to merge those together. So that's why we initialize this with nothing, and when new number coming in, we want to do the union. So if the number is not in our set, UnionFind set, we do an insertion. Otherwise, after we do that, we will try to union it with the number 1 larger, and also try to do the union with the number 1 smaller. So yeah, since that we're still doing going back to do the union by size, at any given time, if we want to query the maximum size for the longest consecutive integer numbers, integer sequence, we can just look into the size to grab that, and this convert our code into a online version. So the numbers come in at different times, and at any given time we can do a query for the sizing information, and the runtime is still in the linear time territory. So let's see if it works. Of course, this online version would also work in the offline kind of fashion, but it's convertible into a have this one iteration to be its own function call, and have this return to be its own function call. So it will work with a string of numbers instead of a set of numbers that's given us ahead of time. So that's so you see that the UnionFind it's quite adaptable, and the code is pretty simple except of the UnionFind itself. But I suggest commit this to memory, how to code UnionFind into memory. Yeah, so there's some extra optimization we can do on the online version as well. So, but this UnionFind solution can lead us to there. So essentially, for that solution, we're just going to maintain the mapping between the number and the sizing information about the longest subsequent that containing that number. So instead of doing this union with the larger and smaller, it's going to looking at both sides and try to combine them, but only looking at the size, updating the sizing information. So it will be a little bit complex and not very easy to think about under pressure. But UnionFind, it's pretty brute force, I would say. Just apply it for number, you insert and do union. And that's all. All you need to know is remember this, and you see that it's quite adaptable from offline to online solutions. Yeah, so that's the question for today. Applying UnionFind to solve this very classical question 128, longest consecutive subsequence. All right.